Welcome to the Explainer. So today we're going to dive into a concept that's, well, it's everywhere. It governs everything from an ice cube in a glass to the very air we breathe. And here's the crazy part. It's all about a world of super intense, high-speed action hiding right behind what looks like perfect stillness. All right, let's jump right in. So you look at this glass of ice water, right? It's sitting there at its freezing point, looking totally peaceful. But what if I told you that calm is, well, it's a complete illusion? Because on a level you just can't see, there's this constant, almost furious exchange happening right where the ice meets the water. So on the big picture level, what we can actually see, nothing seems to be changing at all. The amount of ice, the same. The amount of water, the same. The temperature's not budging. But if you could shrink down to the molecular level, oh boy, it's a completely different story. Okay, so let's zoom way in on what's really going on. This micro view, it shows everything. You've got water molecules from the liquid that are constantly smashing into the ice and sticking to it. And at the exact same time, you've got molecules from the ice that are managing to break free and escape back into the water. It's these two opposite things happening at once in this perfect, delicate balance. This whole idea of invisible, balanced activity, that's really the key to understanding what we call equilibrium. But, and this is a big but, not all balance is the same. Let's dig into the difference between a system that's actually truly stopped and one that just looks like it is. So on the left here, you've got what's called static equilibrium. Just think of a perfectly balanced scale, right? No movement, nothing. Everything's just at a dead stop. Now, look to the right. This is dynamic equilibrium. And the best way to think about it is like two people shoveling sand back and forth at the exact same speed. The sand piles, they never change size. But man, there is constant nonstop activity going on. So here it is, the big takeaway. In the real world, equilibrium is almost always dynamic. That glass of ice water we started with, it's not static at all. Nope, it's in a state of dynamic equilibrium. The speed of the ice melting is a perfect match for the speed of the water freezing. That illusion of stillness, it's hiding this perfectly balanced two-way street of activity. Okay, but you might be thinking, how can we really be sure this invisible action is happening? It kind of sounds like you're just asking me to believe you. Well, the great thing is we don't need to take it on faith. We have science. So let's walk through a really classic experiment that actually lets us see and measure this dynamic process. Okay, so here's the setup. We start with a sealed box, totally dry inside. Then, we put an open dish of water in there. Right away, water molecules start doing what they do. They escape from the liquid and turn into a gas, what we call vapor. Now, this vapor starts to create pressure, and we can actually measure that pressure using this neat U-shaped tube of mercury. It's called a manometer. And this is just a perfect illustration of the whole process. Look at the first panel. At time 0, there's no vapor, so the mercury is perfectly level. Simple enough. Now, move to the middle panel. Evaporation is happening, the vapor pressure is building up, and you can see it's pushing the mercury up. But notice that other arrow? That's condensation. Some of those vapor molecules are starting to turn back into liquid. Then, in the last panel, everything changes. The mercury level stops rising. It's just holding steady. So what gives? And this leads us to the million-dollar question, why did the pressure stop changing? Did the water just stop evaporating? The answer is a huge no, and figuring this out gets us right to the heart of what dynamic equilibrium is all about. Let's break this down with a graph. See that straight line? That's the rate of evaporation. It's basically constant, because it just depends on stuff like temperature. Now, look at the curved line. That's the rate of condensation. It starts at 0, makes sense, right? And then it climbs up and up as more and more molecules fill the air. And then, bam! See where they meet? The rate of condensation has caught up, and now it perfectly matches the rate of evaporation. That, my friends, is our equilibrium point. So there's our answer. The pressure isn't constant because things stopped happening. It's constant because the two opposite processes, evaporation and condensation, are in this perfect dynamic balance. Think about it. For every single molecule that flies out of the liquid, another one flies right back in at the exact same time. It's amazing. Now, this isn't just some cool fact for a science lab. Not at all. This whole principle of dynamic balance is absolutely fundamental to our environment and even to our very survival. Seriously, it's happening all around us and even inside of us every single second of every day. Just take a look at this. The way our blood carries oxygen, it's a gorgeous example of chemical equilibrium. So in our lungs, this stuff called hemoglobin grabs onto oxygen. Then, when it gets to our muscles, the equilibrium shifts and it lets the oxygen go. Perfect. But look at the bottom half. This is where it gets scary. Carbon monoxide can hijack the system. It binds to hemoglobin way, way more strongly, creating this new, deadly equilibrium that literally starves our bodies of oxygen. It's a pretty stark reminder that getting this balance right can be the difference between life and death. And get this, equilibrium is super sensitive to its surroundings. If you just leave a glass of water out on the counter, it's an open system, so it'll never reach equilibrium. It's just going to evaporate until it's all gone. And hey, have you ever tried cooking at high altitudes? The air pressure is lower up there, which totally messes with the equilibrium point for water. It actually makes water boil at a cooler temperature. That's why it takes forever to cook your pasta in a place like Denver.
Okay, so we've been on a bit of a journey, right? We've uncovered this hidden world, we've wrapped our heads around the main idea, we've even seen the proof and talked about why it matters so much. I know it's a lot to take in, but it really all comes down to a few simple, super powerful rules. Let's pull it all together.
All right, here they are, the 4 golden rules of physical equilibrium. Number 1, it has to be a closed system. Nothing gets in, nothing gets out. Number 2, the 2 opposite processes have to be happening at the exact same speed, simultaneous and equal. Number 3, all the stuff you can actually measure, like pressure or temperature, it has to stay constant. And finally, number 4, maybe the most important one of all, always remember it's an illusion. That system is always dynamic, always active on that tiny molecular level. So, now that you know this fundamental principle, I promise you, you're going to start seeing it everywhere. Think about a can of soda. It's in equilibrium, right? Until you pop the top and everything goes crazy. Even the humidity in the air is just a delicate balance between evaporation and condensation. What seems totally static is so often a world of frantic, perfectly balanced activity. So my question to you is, what other illusions of stillness will you see differently now?